Okay, we are up to 44, 45 participants. Probably you can already hear me again.
Yeah, Dr. Jargan, I have made you the host.
Okay.
Yeah.
You can do one more thing. You
Yes.
can disable the annotation from the student there. So
Disable what?
disable to don't allow the student, don't allow the participants to write anything on the screen there. So that's the feature there is available in the participants. You can see there
Yes.
bottom 3 dots there.
Yes.
If you select that 3 dot,
Okay.
there's an option called disable NOS there.
There's mute participants on entry, allow participants to unmute themselves and so on. Disable what? I don't see that.
I think that's there in just a sec. I'll see that part. Okay, continue. Fine, continue.
Okay.
We'll request the participants not to write anything on the screen there.
Oh, that's what caused
Happened
the
initially.
yeah, I see.
Okay.
Yeah, I don't see that option, but
Okay, person Jagan, now you can start. It's already 50
okay.
participants there. You can start now.
Okay, all right. I'll go back to Odyssey, share the program again, and now dive a little bit into the other content of the program. So the Stockroom is the sort of a naked model that you can work with. Sort of the next level of content would be demonstrations. That's on the button here, which is very tightly framed little topics that are addressed, questions literally that you see here with a question mark, and that are answered basically by looking at a particular model, and sometimes involving a couple of mouse clicks, but not a lengthy lab, but something that can be done in just in a couple of minutes, or it's not something an hour-long exercise. For example, how different are ice and liquid water? So if I select that here, so what comes up is a page with 2 pre-built models, one for ice, one for liquid water. They both have dynamics buttons below them. Here's the ice structure, and here is the water model. You can only run by default. You can only run one model at a time. The one with the red frame around is the selected one. If I click on the left side, the red frame is around the ice model, and I can run that one. If I click on the right side, the red frame is around the water model, and I can run that one. I can also do both, though. Sort of override it by, if I go to the compare button, which is here, and select synchronize, and now I'm running both simulations at once. So we don't enable that by default, because obviously this is you're using even more of the resources of the computer. To running 2 simulations like that simultaneously is more time consuming. Things will slow down. So here's the little text on the right side that talks about the density difference, makes the user here change the styles. So here's the hydrogen bonding and the ice lattice, which we can see here the hexagonal structure of ice 1H, and here the for water, which is amazingly similar. Here the density difference, if I select it here, 0.93, there's a little table here below, 0.99 for water, 0.93 for the ice sample. Here there's a question around the simulation of the 2 samples. Does the network, often misconceptions about, does the how different is water from ice? Is it just chunks of ice floating around? No, it's not chunks of ice floating in water or anything like that, but there are great similarities. The coordination number is 4 on average, almost about 4, is just as in ice. And here, a neat thing for ice here is if I put this here on space filling, oops, I had selected an atom, so it only changed the style of this one hydrogen atom. I have to go to edit, select all, and then go to space filling. So now, the ice lattice, the channels, you can look all the way through. So that's sort of a hand-waving illustration of why ice floats on water, because it's such an open structure, which is very unusual for solid structures. So there are other demonstrations. Here, this here is about surface tension. This is simply a layer of water. If I run this, and if you run it long enough, it will form gradually turn into a sphere, because we do doing physical modeling, and surface tension will kick in automatically. And here, vapor pressure illustration. This is a 2D model, very unusual. They have 99.9% of the models in the program are 3D, but once in a while, 1 in 500 models or so will be 2D here, illustrating the temperature dependence of the vapor pressure. Here, limit of saturation for salt and water. On the left side is a standard solution, 1 molar sodium chloride. On the right side, 6 molar, which is, and here you see, this is here now why activity coefficients and stuff like that become relevant for solutions, because if you get to concentrations like that, the ions are no longer infinitely far away from each other. They are awfully close to each other. Even in the one standard solution, they are just maybe 3-4 water molecules between any 2 ions at any given time. Okay, that's the theme of demonstrations. Next, we go to labs. So these are, and this here are highlighted labs. I can switch you to complete list. There are about, a little over 100, I think 115 if you counted, labs, which are worksheets, which are now take a little more time to work through. They include questions. It's a computer lab using physical modeling, not a computer lab using toy models, but using real physical modeling. For example, if I go here to reactive collisions between molecules, here is the reaction here is shown on the right side. It's a little bit, it's not a household reaction, nitrogen difluoroxide and fluorine, but it's something that we have worked out in great detail. If I run the simulation here, they will bounce off, because even though we put enough activation energy into the system, it's above the activation energy, the steric factor wasn't right. So the whole lab is framed this, doesn't explain what I'm going to do now right away, which is students are supposed to, to discover that, through trial and error. And if I do it like this, here I'm getting a successful reactive event. If I do this one more time, this time though I will lower the energy that I put into the system. Energy, total energy. Here by default there's 67 kilojoules more in there. If I lower this to 10 kilojoules per mole, let's say, if I run this, they will immediately fly a little bit more slowly because there's less kinetic energy. And even though this is the orientation which will otherwise lead to a successful reaction, here so we are below the activation energy and it's unsuccessful. So this is obviously a fundamental topic in kinetics. This here is all coached in terms of a worksheet that you see here, where there are questions which the student can fill in. Here, do something random here. There are instructions, that sort of walks you through. I mean, it's a guided lab. It's not, you don't have to invent everything from scratch. It's a guided lab, but the questions can only be answered by working, really with the program. So it's a classical active learning. And in the instructor's version of the program, for which you have an activation code, you can throw up the answers here in the upper right corner, and the answers are shown. The student version, if you get the program for a student lab, this, of course, this wouldn't be available. So it's and it's not hidden in the program somewhere. It's simply not available, and so this option is only available for the instructor to get the answers. Let me show you one more lab here in the chemical bonding. Explore bonding and ionic compounds. So here's Dr. Kishore had shown earlier the sodium chloride structure, which he had changed to potassium bromide, I think. So here we are also going over. So here we are now going to make sodium chloride from scratch. Basically, here this is a system, gas phase system. You could think about that as sort of two flavors of argon: argon that is yellow and argon that is blue. If you look at the periodic table, I mean, sodium chloride. Oops. There's always now if I want to get to the toolbar, the zoom bar sits on top of that. Okay, no, I think I can do it here. So if I go to the periodic table, so argon, of course, sits between chloride and potassium. So if I do, let's say, two flavors of argon. Now, what I can do is, if I could put charges onto the system, if I put here, for example, these are uncharged. So if I put here positive charges on both, so I get this type of behavior. And this is all in the worksheet. It takes a while to get to that step. I mean, I'm giving it all away by immediately doing, the teaching purpose. Here is the plus minus, so Coulomb's law at work. Ionic bonding is a lot easier to understand than covalent bonding, because if you take the ions as the substituent particles, everything else then is classical, just Coulomb's law. So if I stop this here, and so I compare this structure here, for comparison, here's sodium chloride. That, of course, is, and here is what I created from scratch, and here's the sodium chloride structure. Here in this worksheet, there are other examples of solid structures, and then here are the instructions basically, and here are the questions. Describe your observations, compare the observations for the case of A with case B, and so on. And so it's a total of 16 questions that will take a student some time to work through. I'll show you one more section, and then wrap up the ODYSSEY part of the workshop. I'll go to the home page and go here, miscellaneous. So that's a section of the program where where you see models, little essays about all kinds of topics. This does not map directly on the standard sequence of a general chemistry book, but interesting topics from the real world of chemistry. If I go here to pharmaceutical chemistry, where's pharmaceutical? Down here. Top 10 prescription. If I go here to pain medications, let's say, here's aspirin, ibuprofen, naproxen, acetaminophen or paracetamol in India. So models for that. I want to here in this context here, you saw how you can build with the builder. Pretty much anything from scratch. Dr. Kishore already built glucose, which is not really the beginner's molecule. And I'll now show you something that I built in advance, because it would take me a few minutes, but it wouldn't be rocket science to do it. Namely, the one drug that now At least I don't know how much attention it's getting in India, but here in the US now, remdesivir is the unlike hydroxychloroquine that Trump was pushing, where it seems to be patients seem to only get sicker from it. This seems to be the one drug which actually seems to have at least cut down on the recovery time. So people can get out of the intensive care more quickly. So it's this molecule here, which I just built from scratch, using the advanced builder of the programs, just along the lines that Dr. Kishore did for glucose. And actually, this is still a little bit complex. This here gets metabolized to something doesn't have a name, this is actually sort of the active metabolite, which has this ugly name, GS441524. The company that's making this stuff, Gilead, I guess never gave it another name. It continues to be called GS441524. So this here now is amazingly similar, and this is why it has to do with its biological action with adenosine. But do a side-by-side comparison with something I will now get from the stockroom. Search for more systems. And I will type in here adenosine. So one of the, which appears, of course, in one of the 4 bases, both for RNA and DNA. RNA is the relevant one for the coronavirus. I do here adenosine molecule. So this came from the stockroom. This here I built from scratch. You can go to Wikipedia page or something like that. So, and this here, the style here, this one from the stockroom here, it highlights the heterocycle here by using the tube style. Now to make it an apple-to-apple comparison, I will do a select all and change all this here to ball and spoke on both sides. And now I can compare them. So if I here do this, if I really want to compare them, I want to sort of make them look similar. I can select this. You see a little bit what you can do with it. It's all explained in the tutorial pages. If I hold down the Alt key, I can rotate around this. Now I can make, now you can see here. And now superficially, it's exactly the same. There's some small differences. There's here, the drug here has a cyano group here. And here there's a carbon-carbon bond. Here's a carbon-nitrogen bond in here. And here this 5 ring, here it's just 1 nitrogen. Here there are 2 nitrogens. So otherwise, they're just 2 small differences. But that seem to make all the difference. So I mean, this molecule apparently it's an inhibitor for the for RNA dependent polymerase. It stops basically the replication of the virus, not immediately, but after. This is basically replace one of the A's in the RNA chain, then another 4 get attached, and then it comes to a stop. So for reasons I don't quite understand, it stops after 4 more steps, with chain length of 5. Okay, so that's shows you, you can use the program, the build functionality. It's an open-ended program that can be used for all kinds of things in a teaching context. So you can go with what you could call canned content, demonstrations, labs, or you can do your own thing, which I just gave you an example of that. I want to wrap up I want to show one more thing about ODYSSEY, which is go back to the or use that to wrap up the ODYSSEY part. I have to do change the share. Stop the share and share my screen again for the PowerPoint share. and go here to, so molecular dynamics simulations are, which you've seen several examples of. I'd like to sort of point that out, is actually is something that's a technique which is a lot older than people think. It all started out in 1964 by Anis Rahman, who was born in Hyderabad, actually came back to India after getting his PhD in England, but eventually went to the US and died, unfortunately, at the young age of 59 from cancer. He would have been a shoo-in for the Nobel Prize. In 2013, then Nobel Prizes were in fact awarded in this area. He just didn't get to see it. So if you see here, the billion particle simulation, first billion particle simulation was already 23 years ago. Right now, I want to show you quickly here is now even simulations are carried out for the coronavirus, and one could really say it's high time to start to use MD in education, which it's a completely unknown. ODYSSEY is the only game in town that allows you to do this really. If I go here to here on the topic of these coronavirus simulations, it's a lady from the University of California, San Diego, Romy Amaro. These are massive simulations. It's an all-atom model of part of the virus envelopes, 200 million atoms, nanosecond time scale. And with ODYSSEY, you can also get to the nanosecond time scale if you run for a few hours, but not for 200 million atoms. You can do it for 200 atoms. And this is all running on 250,000 cores. One of the largest supercomputers in the world at the University of Texas. So here, I'll quickly show you here the brand new thing. So this is the spike protein. It's not the entire virus, it's a huge thing, but it's the of the envelope. You can see here it's one of these spikes, and you can see if there are all kinds of observations one can make about the accessibility here for drugs, for solid molecules. This is 200 million atoms behind this picture. Massive effort, but this is sort of state of the art. So no, people sort of are surprised by that, but the program that Romy Amaro used for that is called NAMD. It comes out of the University of Illinois. The force field which is used is called CHARM, which is basically just sort of something different from what we are using. There are reasons why we are not using CHARM. We are using something else. The water model is just ours is actually a little bit better than what they are using. Timestep time technique is the same. The main difference is here. The processors, the computer that I'm using now.
International anninchi break nu cut ayipodusdi. Link vachi 4வது link ichundaru.
Maybe I should mute the computer I'm using has just two cores. It's an i7 chip. The computer that you use is 250,000 cores. And is there something here to? Oh no, it stopped. Mute. I don't see the option now where I can mute everyone.
Just go to Dr. Geraldine. Just go to manage participants. There are 67.
I have this.
Just go there, and at the bottom it says mute all.
So they are muted, sir. You can continue. Nobody is now online. Dr. Dissu, can you mute your mic, please?
Yeah. Okay. All right. Okay. Maybe we can. I saw it earlier, but it's like right now I can find it. So here I'll go back. My slide is still there. So I'm using 2 cores. Those simulations were on 250,000 cores. I'm using an off-the-shelf laptop. Any modern laptop will do. The cheapest Windows computer will do. And don't ask how much that costs, these simulations. So it's but that's the frontier of using these techniques. By using a tool like that in teaching, you're actually exposing students to something that is right at the frontier. And the I will actually show you this. Here you see, I mean, it's a teaching tool that is not a toy. Most electronic teaching tools are toy-like. This is not. So because there's a direct correspondence between, I mean, this it's all, we keep it all easy. We keep, just push 2 buttons and it will all work. But the underlying, under the hood, it's very similar to what you use in the world of research. Here another aspect of using ODYSSEY in teaching is that here, this is just a title page I got from this month's issue of the Science Teacher, which is one of the journals of the National Science Teachers Association in the US. And this is about something in biology, not chemistry, but I love the title, Messy Data, Real Science. This is something that often falls by the wayside, in teaching, because and which is such a problem then for students when they transition from undergrad, to graduate school and have to do research, and all of a sudden feel completely lost because they have to deal with messy data, not with perfect textbook things. ODYSSEY will give you will expose you to messy data by design because it's based on real physical modeling. Okay, I'll close this, and we had planned on having a question and answer session before transitioning to Spartan. Should we?
Dear participants, you can unmute one by one yourself if you want to ask direct question, or you can type in the chat window also. So we will revert back to you. There is one query from somebody, Dr. Jargan, regarding reaction mechanism. You can, I will just repeat what is the question.
I think just a minute. Participants can also raise their hand using the chat window, and accordingly, Dr. Jargan can then unmute you. That is,
okay.
That possibility is also there.
Dr. Tamil Selvi want to ask, can we show the transition state and progress of reaction while teaching reaction mechanism?
Yeah, there are pre-calculated examples in ODYSSEY. You can do all this from scratch, open-ended with Spartan, the next program we are going to show. But if you're in ODYSSEY, I'll go, and I have to share it, right? Or share, yeah. So here, I'll go here to the lab section and kinetics, examining a reaction mechanism. This is an example which was calculated with Spartan, which the hydrolysis of the fluorine equivalent of phosgene, COF2, giving you carbon dioxide and HF. And I can here do an XY plot with the reaction coordinate on the x-axis, put the relative energy on the y-axis, smooth fit, and here, if I now scroll through, you see this. I mean, there's one transition state, intermediate, another transition state, another intermediate. It's amazingly complex. In real-world examples, kinetics is very, very complex. But this is what textbooks, love so much to stick to 8+3. Okay, so this is we can do something like that. Also, open-ended in Spartan.
Yeah. Please mute. Someone is Dr. Karani Anupa. We are getting a background noise from your side. Please mute yourself. We have a question from Jabir. Can Jabir we can unmute Jabir? Dr. Jagan, you can see there is a name. J.I. Yeah, he raised his hand. Please.
Am I audible?
Yes.
I'm not in the view with, I only see six tiles right now, so.
No, that's
okay, please go on. Let's
Jabir, you are audible now. You can carry on.
Yeah, thank you. Very nice presentation that you gave. Like, it was amazing, and like that's one thing that I'm try to asking is, like, I'm a PhD research scholar right now, and
yes.
I want to ask, like, in in the real research publication, can we
Yes.
use this simulation to get some insight, or to use this in our in our research papers also? Can this is up to that
Yeah.
mark, or it's just like
Yeah.
to not to that mark? Yes.
Okay, that's in the case of Spartan, which is a program we'll get to in the next remaining 20 minutes. That is absolutely the case. Spartan is used all over the world as this is its origin. It's a hardcore research program. In the case of ODYSSEY, ODYSSEY was designed as a teaching tool. So there are certain compromises there in terms of the force fields. ODYSSEY allows you to simulate from hydrogen to DNA, everything with one interface. You won't get typically, research quality, simulations of something. It's good for exploratory research, for doing sort of, to get a feel for systems. But you wouldn't use ODYSSEY at that point, for running trajectories of system, of a new research system. For that, I have to point you back to one of these other programs, of which there are many. NAMD, for example, which is the one which is used by this lady in San Diego, but which is used by thousands of people around the world. There's a learning curve for that, and having worked with ODYSSEY will cut down on the learning curve, but for real research, you will eventually have to use one of these other programs.
Okay, thank you.
There is a question from
Different
Dr.
from
V.
different from Spartan. Spartan is the best you can get. So I mean, for quantum chemistry.
Dr. Jagan, there is a question from VS Gueri that is it possible to take a snapshot of the molecules when we build molecules? It is possible to store their coordinates in different file formats.
Yes, you can. If I do here, I've if I go back here to I don't know, molecule of propanoic acid, and I can go to file sample as. I have the choice here of XOD data, which is the native file format, and I have the choice of SP input, which allows me to export it to Spartan, to the quantum program. It does not give you all the other. I mean, SP input would allow you to via Spartan. Spartan has a long list. You can, I mean, if you want to prepare it for some other quantum program or something like that, you would have to go through Spartan for that. In a teaching program, that is not a really consideration. You have for pictures, you can have, you can save images, bitmaps, and JPEG and PNG and all that stuff. So, it's a teaching program, not a research program. Okay.
Dear participants, fourth link is ready. This meeting will end in next 6 minutes. So we will keep on talking and discussing on your problem. Once it is closed, we will move to the fourth link. Please look in the chat window. Thank you.
Okay. Because that,
Yatin, in this session, let's have only the question answer. In the next session, we'll briefly go through the Spartan. Already we have 3 sessions done there. Now we'll have some question answer. One more announcement to the participants. I have written that in the chat thing also, that for getting the certificates, you have to practice this. You'll get the 30-day trial of this particular software from Mr. Yatinder. Don't worry about that. But for getting the certificate, you have to practice this. And I tell you that it's not the thing of certificate. Once when you practice this, then you will be in love with this particular software. So go and practice the software, minimum 3 different models. One from inorganic molecule, one organic or biomolecule, or one from solid state, minimum. But try to go through that, try to create some interesting sample and send it to us, and then only we'll issue the certificate. This is for the ODYSSEY. The same thing will happen for the Spartan also. So once we'll have that Spartan thing, and then we'll give you that assignment based on that Spartan also. Fine. But I'll tell you that it's very user friendly. Within a couple of hours, you'll be comfortable with this particular software. So don't worry about that. And we'll share the trial test.
Yeah, we have a question from Dr. Indrapal Parisa. Is it possible to show the progress of pericyclic reaction can we show modes of rearrangements?
Yeah, yes, but that you really you really should use Spartan for that. So that is something. Now you're getting into hardcore organic chemistry, and you need the open-ended functionality of Spartan. So Odyssey would not be the appropriate tool for that, for something that specialized.
Dr. Indrapal Parisa, we are presenting two software here. The Odyssey is going to over. Now we will move to the second software called Spartan, where we will answer your query.
Yeah, I can maybe, can I see, we have 3 hours, 45 minutes. Maybe I can quickly, I'll switch. I can do a screen share for what you would have seen in the video that Dr. Kishore aborted in the beginning.
There is a question from Divya Raja. Did you send some sample question to prepare assignments? Okay.
Yatin.
Yeah.
Yatin, let Professor Jurgen share that video, means which he had recorded earlier, which was not audible from my side. Let's see from his side if it is audible.
Okay, we just show the slides. You know, they were contained in the video. So then I can make it. I can really have 3 minutes 9 seconds left. So
we are playing with Zoom.
So I have 3 slides, 1 minute per slide. So the company is called Wave Function. So we have been around for almost 30 years. Was founded by Warren Harry. Warren Harry was the probably the most famous student of John Popel. You may recognize John Popel as the Nobel Prize winner in 2000. I forget now which year it was. 2000 was no, it was the late 90s. With Warren Harry was the first student who actually wrote the original code of another quantum chemistry program called Gaussian. So it was a spin-off of the University of California, Irvine, and this is still where we are headquartered. We have a sales office in Tokyo. There are just 15 people. So so we are a small company. So I think we are doing well being so small. So the mission is make molecular modeling easy and accessible. So by using an intuitive GUI, all-in-one approach, and minimize or even eliminate technical jargon. So promoting standard methods, that's always important. 3D visualization, this is the title of our workshop. It's sort of self-explanatory. Pictures, replace 1,000 words. And finally, bring scientifically sound modeling to the world of teaching. There's a lot of modeling in the world of teaching is not that scientifically sound. It doesn't mean it's useless, or it really often has its place, but it should be complemented by something that's based on real science, which Odyssey and Spartan accomplish. So they are the 2 programs. So I have 1 minute left here. Odyssey we've now heard about. It's an education program. I said that now repeatedly. Its user base is about half in higher education and half in the high school world in the US, advanced A levels in the UK, and so on. The other program, no, we'll get to Spartan. So the flagship program, which is actually a collaboration with another small company called QChem, has its use. Originally was all research, but now it's also used in education. But typically in the second year of college, organic chemistry, physical chemistry, not so much in general chemistry, and continued heavy use, and all the pharmaceutical companies use it. It's the chemical industry, Exxon, and all those there. We have copies all over the place. And I probably on the last 10 or 20 seconds, so I'll just stop and wait for the annihilation.
Yeah, everybody please get on to the 4th link. I have already copied it into the chat window.